Okay, good evening to one and all. Today I am going to discuss about the Booth algorithm. What is the main function of the Booth algorithm is? So Booth algorithm is the algorithm which is used to multiply numbers represented in 2's complement form. 2's complement form. So that means whenever you are going to multiply the numbers which are represented in 2's complement form, then this is the best algorithm. This is the best algorithm to represent. Okay. Now, now see here, the main idea behind this Booth algorithm is, okay, first, if you take any two numbers which are represented in 2's complement form, so here there are two types of numbers. Okay. So that means a number which contains a string of zeros in the multiplier. So that means to perform multiplication, we require multiplicand and multiplier. Okay, if there are string of zeros in the multiplier, there is no need to perform addition, but just by shifting and a string of ones in the multiplier from the bit weight 2 power k to the 2 power m can be treated as 2 power k plus 1 minus 2 power m. So that means when the multiplier contains a string of ones, okay, so that means if you take binary number, there are weights, okay, like 2 power 0, 2 power 1, 2 square, 2 cube, like that. Okay, if you if there is a string of ones from 2 cube to 2 power 1. Okay, so that means here from 2 power k to 2 power m. Okay, so they can be represented like this. Okay, so that means 2 power k plus 1 minus 2 power m. So here what is the value of k? The value of k is 3 and here the value of m is 1. So if you substitute those values, so 2 power 3 plus 1 minus 2 power 1. So 2 power 3 plus 1, which is nothing but what here? 16 minus 2, which is nothing but 14. So that means the multiplier is nothing but 14 here. Okay. If you take an example. Now, for example, if you take the binary number like this, 4 ones, there is a string of ones. There is a string of ones from 2 power 2 power 0, 2 power 1, 2 square, 2 cube. Okay, has a string of ones from 2 cube to 2 power 0. So that means here, what is the value of k? The value of k is 3 and the value of m is 0. Now, the main steps involved in the Booth algorithm are the Booth algorithm needs the examination of the multiplier bits and shifting of the partial product. Now, what do you mean by the partial product here? So, partial product is nothing but, so whenever you are performing the multiplication, now I would like to take one example. So I am going to multiply 14 with 14. Now, 4 fours are 16, 1 fours are 4, 4 plus 1, 5. Now, this is nothing but what here? Partial product. So that means indeed multiplication involves the generation of the partial products. Okay, so that means when you take all the partial products, if you want to get the final product, you have to add all the partial products to get the final product. Okay, so here also the Booth algorithm needs to examine the multiplier bits and shifting of the partial product. So prior to the shifting, so that means before shifting, the multiplicand is added to the partial product or subtracted from the partial product are left unchanged. So here there are three conditions. So the first condition is the multiplicand can be added to the partial product or the multiplicand subtracted from the partial product or it left unchanged by following the three rules. Okay. So the first rule here is the multiplicand is subtracted from the partial product when we get the first least significant one in a string of ones in the multiplier. So that means you are going to multiply. So whenever there is so the string of ones is nothing but a consecutive ones. Okay, like this, a string of ones. Suppose if the multiplier is 0, 1, 1, 0. Okay, so this is nothing but a first one encountered in a string of three ones. So whenever that one is encountered, then the multiplicand is subtracted from the partial product. Next, second case, the multiplicand is added to the partial product when we get the first zero. Okay, provided that a string of zeros in the multiplier. So that means here this is a 1, this is 1, and this is also 1. So after this one, string of ones are ended. So that means the next bit will be nothing but what? 0. Okay, so when 0 is encountered, then immediately the multiplicand is added to the partial product. So there was a previous one. So the last case is the partial product does not change when the multiplier bit is same as the previous multiplier bit. So that means 0, 0 or 1, 1. Here the possibilities I am explaining: 0, 0, one case, 0, 1, one case, 1, 0, one case, 0, 0 and 1, 1 both are belonging to the same case. So that means when the multiplier bit is same as the previous multiplier bit. Okay. Now this is the hardware required for the Booth algorithm. So we require one register, BR register, and we require one accumulator register, and we require one QR register. I will tell you what is the purpose of these registers, and we require one complementer and parallel adder. Okay. Now, so complementer is nothing but, so it is going to perform the 2's complement. Okay. Now there is a counter. Okay. There is a counter, sequence counter. Okay. So initially the sequence counter is set to some value. So after every iteration, the sequence counter is decremented and it is checked whether it is 0 or non-zero. If it is 0, end the process. If it is non-zero, then repeat the process. And Qn is nothing but, here I am showing the Qn. What is this Qn is? The least significant bit of the multiplier. Okay. And the Qn plus 1 is the extra bit. Okay. So Qn plus 1 is the extra flip-flop. So initially it is set to 0. We'll discuss it later. Okay. So this is the hardware required for Booth algorithm. And now we will see the flowchart. Okay. Now, if you see the flowchart clearly, start. Initially, we need to store the multiplicand in BR register and multiplier in the QR register. And initially, we need to set the accumulator, which is nothing but AC register to 0. And Qn plus 1, I already told you initially it is set to 0. Sequence bit, sequence counter. Sequence counter is set to the number of bits in the multiplier. Okay, now suppose if n is equal to 5, then the sequence counter is set to 5. So if you represent 5 in binary, so which is nothing but 1, 0, 1. Okay, so after that, we need to inspect the values of Qn and Qn plus 1. I have already discussed the three previous conditions. Okay, so that means we have to inspect Q suffix n and Q suffix n plus 1. Okay, so the four possible values are 0, 0, 0, 1, 1, 0, 1, 1. Okay, so when these two bits are 1, 0, then what will happen? So AC becomes AC plus BR bar plus 1. So which is nothing but what here? AC plus BR bar. What is BR bar? 1's complement of BR plus 1. So which is nothing but the 2's complement of BR. So that means, what is the meaning here? AC becomes AC plus BR bar plus 1 is nothing but what? 2's complement. 2's complement of BR. So simply what is the meaning here? Subtraction using the 2's complement. So which is nothing but AC becomes AC minus BR. Okay. Now, next, when Qn and Qn plus 1 are 0, 1, then what is the meaning here? So that means AC becomes AC plus BR. Previously, I told you the conditions, three conditions. One condition is the multiplicand is subtracted from the partial product, or the multiplicand is added to the partial product. So these are the two conditions, subtraction condition and addition condition. So when the Qn and Qn plus 1 are 0, 0 or 1, 1, So that means when these two are same, okay, so it can be either 0, 0 or 1, 1, then there is no change. So the partial product remains unchanged. The partial product remains unchanged. So after performing, suppose let us assume if Qn and Qn plus 1 are 0, 0, nothing will happen to the partial product. Simply, you are going to perform one operation that is called ASHR. What is ASHR? Arithmetic shift right operation. Now, why should we use the arithmetic shift right operation here is to preserve the sign bit. To preserve sign bit. So that means before shifting, if the sign of the number is positive, after shifting also the sign of the number remains same. Like similarly, if the sign of the number is negative before shifting and after shifting also, the sign of the number remains same. So after performing the arithmetic shift right operation, then the sequence counter will be decremented by 1. So one iteration is completed. So that means the sequence counter is decremented by and SC becomes SC minus 1. Okay. So after decrementing the sequence counter, you need to check whether the value of the sequence counter is 0 or not. If it is 0, then end the process. If it is non-zero, again repeat the process. Okay. So this is the flow chart for the Booth algorithm. Okay. Now, this is nothing but one example. Okay. We are going to multiply the two numbers. One is -9 and another one is -13. So I already told you initially QR contains multiplier. Okay. QR contains multiplier. Okay. Now here, what is the multiplier? -13. But -13 has to be represented in which form? 2's complement form. So first you represent +13. Okay, using 5 bits. So 0, 1, 1, 0, 1. Okay, so this is +13. What is -13? -13 is take the 2's complement of this one, which is nothing but 1's complement, 1, 0, 0, 1, 0, plus 1. So which is 1, 0, 0, 1, 1 that the QR contains. Okay. Next, -9. What is -9? Multiplicand. Multiplicand is stored in which register? BR register. Now, how to represent -9 in 2's complement form? So first represent +9, that is 0, 1, 0, 0, 1, and take the 2's complement of this one, which is nothing but 1's complement plus 1. How do you find the 1's complement of a number? Replace 0 by 1 and 1 by 0. So which is nothing but 1, 0, 111. Okay, so this is nothing but BR. Now it is BR bar plus 1. Okay, so that means if you take the 2's complement of +9, which is nothing but -9. Again, if you take the 2's complement of 9 -9, which is nothing but +9. So 0, 1, 0, 0. So initially Qn plus 1 is set to 0. I'm telling only the one step, rest of the step remains same. Okay. So what is Qn? What is Qn now? The least significant bit of the multiplier. Okay. So what is the least significant bit of the multiplier? 1. Now Qn is 1 and Qn plus 1 is 0. So that means, will it take left arm or right arm? Left arm. Okay now. So in the left arm, AC becomes AC plus BR bar plus 1, which is nothing but 2's complement. 2's complement of BR bar, sorry, BR is added to AC. So what is 2's complement of BR? BR bar plus 1, which is added to AC. Initially, accumulator is clear to all zeros. Okay. So which is nothing but all zeros plus 0, 1, 0, 0, 1. So all zeros plus 0, 1, 0, 0, 1, which is nothing but 0, 1, 0, 0, 1. Okay. Now, what is the value of AC? AC is 0, 1, 0, 0, 1. Now, immediately the next step is nothing but arithmetic shift right of AC and QR, including Qn plus 1. Okay. So, arithmetic shift right of AC and QR including Qn plus 1 means take the content of AC. What is the AC? 0, 1, 0, 0, 1. And what is QR? 1, 0, 0, 1, 1, including Qn plus 1, which is nothing but 0. Now, if you perform the arithmetic shift right operation, if you perform the arithmetic shift right operation, shift right, you are performing right operation. So that means every bit is shifted towards right by one position. This 1 will appear here. This next 5 bits 1 1 0 0 1 will appear here, and this next 4 bits will appear here, and the vacant position is what? MSB. So this MSB is filled with the sign bit. Now what is the sign bit? Are the previous MSB 0? So now it will become 0 0 1 0 0 1 1 0 0 1 and 1. So after performing the arithmetic shift right, AC register will contain 0 0 1 0 0 and QR register contains 1 1 0 0 1 and Qn plus 1 contains 1. Okay. Now after arithmetic shift right operation, what will happen? The sequence counter is decremented by 1. So what is the initial value in the sequence counter? 1 0 1. Now this 1 0 1 has to be decremented by 1. So SC becomes now 1 0 1 minus 1, which is 1 0 0. Now 1 0 0, 4. 5 becomes 4. Is it 0 or non-zero? Non-zero. So when it is non-zero, again you have to repeat the process. Again, you have to take Qn and Qn plus 1. Now what is Qn? 1. And what is Qn plus 1? 1. So like that, you have to repeat the process, okay? And until the sequence counter becomes 0. When the sequence counter becomes 0, the content of AC and QR register combined together is the final product. Okay, now what is the final product now? So what is minus 9 into minus 13 plus 1 1 7? Okay, so what is the result in AC? 0 0 triple 0 double 1. Next here 1 0 1 0 1. Now, so convert it into the decimal form. So add the weights for which the bits are equal to 1. So 64 plus 32, 96, 96 plus 16, 112, 112 plus 14, 116, 116 plus 1, 117. So this is the final result. I hope you understand this one. Okay. So thank you all. Thank you one and all.